Thanks, Kevin, for the introduction, and thank you to Inductively for inviting me to give this seminar. So we're going to be talking about carbonate geochronology, and I'll try and cover some of the basics for those who are kind of less familiar with the geochronological methods and some of the applications. Kind of give you a wide breadth about that. First of all, the people at the BGS, colleagues past and present, have been very much involved in carbonate chronology as well. This is just not a sole venture, and I've worked with over the 15 years at BGS, pretty much been doing carbonate chronology the whole time. So I've worked with a long list of people, some of them, many of whom I would have forgotten to write here. But this is very much a collaborative effort in gaining knowledge in this chronological method. A couple of caveats as well, because I do chronology carbonates. People often think that I am a carbonate specialist. I'm not ashamed to say that sedimentary geology was my least favourite subject as an undergraduate, and carbonates were my least favourite sedimentary rock. But when you've spent half your career working on them, you do learn something along the way. So in this seminar, we're going to a very brief bit about history of this method, some of the fundamentals of the methods that we're using. So this talk is mainly going to be talking about laser ablation, LA-ICP-MS. Some of the techniques and methods we can use in characterizing our samples, some of the limitations in the methods, some of the data that we can help to interpret ages, and quite a bit on applications as well. So this is hatched from a kind of a longer talk that I've given on the history of carbonate chronology. First, it gave this in 2018. I then revised it in 2022 and added on a few years, but I haven't revised it for 3 years, so it's a little bit out of date. I really wanted to start at the beginning and skip to the end. The reason I want to start at the beginning, I do find the history of isotope geoscience quite fascinating. Carbonate chronology in particular, the first worked on at the Oxford lab by Professor Stephen Morbarth. An interesting guy, a German who fled Germany in 1939, spent most of his career at Oxford, and was one of the first geochronologists doing isotope geoscience in the whole world. He was a world leader for many years. So he published in 1987 this paper dating Archean limestone using lead data. This was kind of the first seminal work that led several other labs to try this method. And what I wanted to include really because of this talk, because of this paper, is a few observations he made that were very much relevant for his whole rock lead dating. And these are really relevant to why we use laser ablation today. So particularly this bit of this quote: the great ranges in uranium lead and corresponding lead isotope ratios between adjacent small domains turn out to be a common feature of sedimentary carbonate. And it may be possible to extend the application to dating to limestone throughout most of the protozoa. Well, Stephen Morbarth at the time wouldn't have been aware that we would be in the future doing laser ablation to date these rocks, but it is this kind of variation in the uranium lead ratios, as we'll see much later on, that really allows us to use this technique. This is really quite pioneering. So over the next kind of decade or so, there's various applications. People tried dating marbles. They then went to younger and younger materials, corals. The first kind of ore deposit dated 1996. And then there was kind of seminal work in the late 90s where they applied this technique to quaternary rocks. So the next kind of 10 to 15 years in terms of carbonate chronology, pretty much dominated by dating young rocks, and particularly some high profile studies, particularly because there's a lot of interest in dating some of our ancestors in the caves and the limestones and tuffers that were found hosted skeletal remains. So laser ablation is kind of the focus of this talk. Came around very much in the late 2000s, and there were 2 PhD students working on this. One was based here, Lee, and Martin Whitney was based in Bright Holloway. Both of these studentships were attempting to date in laser ablation. Martin worked on the Alps and basically failed to get any good successful dates. Had it been successful, the early history of carbonate, the laser work might have been quite different. But Lee was successful in dating some cements that we found in ammonites. This work was eventually published in 2014. It's pretty much seen as the first paper for laser ablation, learning those carbonate chronology. We've been using an in-house standard throughout this time, but we didn't publish that for some years. We started kind of talking about these methods kind of throughout the early 2010s, and by 2016 we started seeing kind of tranche of papers coming out using laser ablation. In 2017, we thought we'd better finally actually get around to publishing something on the standards, the reference material we were using. And so this, as I said, this talk I updated in 2022, and these are the numbers papers coming out per year. And if we went to 25, we probably now see kind of over 100 papers a year using this method. But by the kind of 2016, 2017, people were trying to apply it to a wide range of applications in geoscience. So that's a little bit about the history and the timeline. So I'm going to talk about the methods now. So first, we're going to kind of revisit what people call the traditional method or the old method. And this is basically what Stephen Mormark was doing in the 80s and has been sort of refined over the years. This is often referred to as ID TIMS, although actually the measurements aren't always made with a TIMS mass spectrometer, they can be made with an ICP-MS as well. So it involves dissolving chunks of carbonate. These might be drilled out of a rock or cut with a saw. Use various acids to dissolve the carbonate to try and get rid of the organics. And then use column chemistry to separate out the uranium, the thorium, and the lead fractions. These are dried down, and we dry this down onto rhenium filaments. And then these are placed into the turret of a mass spectrometer. And then we measure the isotope signals. This technique is calibrated. Well, the key thing about this method is calibrated with spikes. So these are solutions with known ratios of uranium, thorium, and lead. By using these spikes, the data we get is very accurate and very precise. So even though laser ablation is sort of overtaking this method, we still need to use this method to characterize our reference material. So it's very much still part of the overall package of work. But the method that's kind of overtaking this and is much more popular now is laser ablation ICP-MS. So this involves sticking a polished block or a polished section into a cell of a laser. These are typically X-ray laser systems, mostly everyone's using 193 nanometers. And there are a few variations on that. So you ablate a small spot in this material, and we have a gas and then the helium that carries it through to an ICP-MS. So this is a picture of a crater in a carbonate. This is a sort of 30-second ablation. And people will normally use something between a 50 and 150 micron spot. That's kind of the diameter. Occasionally we can go smaller than that if you have a lot of signal or a lot of high uranium in it. And some lasers do go bigger, up to 200 or even 250 microns. Here's some images of our cell, one of our cells, and these are thin sections we can use, or we can use carbonates in epoxy blocks. Laser ablation system. And we can do the measurements themselves on a variety of ICP-MS instruments. All of these will do uranium lead, and there's some significant pros and cons of using different instruments. The multi-collector instruments, for example, are more sensitive and generally give you more precise data points and uncertainties. On the other hand, the quadrupole instruments are much more flexible. You can measure more elements at the same time as uranium lead, and they're generally quicker to set up. And the single collector kind of sits in the middle and is perhaps one of the most advantageous instruments for this method. So one of the key things about the laser ablation method, and this is sort of applicable really to all chronology, or uranium lead chronology, is that we use a normalization called standard sample bracketing. And this is kind of familiar to a range of different methods as well. The idea being that we have a standard or a reference material, and we're going to measure that throughout our analytical session. So we'll use blocks of 3 reference material run from the sort of beginning until at the end of this session. And this blue line is just one of the signals, the uranium signal here. So we're on blocks of standards, and in between we're going to run our samples. And we're basically going to calculate our measured ratio or signal and compare that with our known ratio. And we're going to correct for that difference. And by using this standard sample bracketing, we can, if there's any drift in time through the session, we can interpolate that with a spline through the data. Now, the reference tools we use, these have certain kind of ideal scenarios of what a reference tool should look like. Ideally, they're going to be homogeneous in isotope composition, and therefore the age. Ideally, if they're going to be homogeneous in our element concentration, that means we know kind of what signals we're going to get from a mass spectrometer, and what spot size we need to use, and what ablation conditions. For a uranium-lead standard, ideally you want to have high uranium and low amounts of lead when that mineral forms. And we want it to remain a closed system. So that means once that mineral is formed, the uranium and the lead isotopes get locked in. And if it's going to be a standard or a reference tool, we want it to be abundantly available enough to be able to share to dozens, maybe even hundreds of labs around the world. And the thing about carbonates is they pretty much tick none of these boxes. So we're going to have to work around these in various ways. And all on the left is just one of our mounts. It's a 1-inch diameter mount, and you can see the carbonate tubing is various. So this is RA138. So this is a recently kind of published standard, and you can see it's texturally, compositionally heterogeneous. You have a matrix, and then we have a spot tree of cement. And when they do chronology of different cements, although they're generally around the same age, there's some variation. So it's not ideal for a standard, but if we're careful in choosing where we place our spots, we get pretty reproducible data. So the fact that natural carbonates are generally heterogeneous in texture, and they can form and can be easily altered, and things like that, means it's actually quite hard to find useful standards from what nature gives us. This is quite different to zircon. So zircon is perhaps the best behaved in terms of uranium-based chronology or in situ chronology. This is data on a very popular, commonly used zircon standard, 900. And you can see the isotope data is generally quite homogeneous. Pretty much whatever crystal fragment you analyze, you get the same composition. We can see that quickly here. The percent variation is very clear. The normalization to this standard is quite a simple process. But if we look at how a carbonate standard looks in the same space as the weather or quality plot, if we look at a carbonate standard, these are our data points literally down here. They don't fall in one place. We can see a line. And that's how carbonates tend to behave. We get a line because they're a mixture of radiogenic lead, that's the lead that we get from the uranium, and the initial lead, that's the lead that formed, that was there when the mineral formed. It's quite hard to see this line on this isotope diagram. So for carbonates and for other minerals that incorporate carbonate, we tend to plot them on a different diagram. This is the Weatherall plot on the left. And what we tend to use is what's called the Terra-Vassavo plot. So here we have different axes for the uranium-lead ratio, the x-axis, and the lead-lead ratio on the y-axis. And these diagrams are actually quite simple to read. Essentially, the initial lead composition is going to fall on the top left, and the radiogenic lead, so that's the lead that comes from the decayed uranium, is going to fall to the bottom right. And carbonates tend to form, or a good carbonate that forms in a single event is going to form a mixing line along this line. We can draw a regression through that. And the intercept down here along the control curve is. So this standard, different fragments of this standard material have different amounts of common radiogenic lead. So standardizing and normalizing to this is actually slightly more complicated than doing something like zircon. It's just the same diagram, again with just more labels. So here's a data point down here. So this one has 10% common lead, so it falls almost on the control curve. Whereas this data point up here has 9%. Right. So some people call these isochrons, other people call them mixing lines. So going back to standard sample bracketing, how do we get around this when we're using heterogeneous minerals like carbonates? At the moment, the community basically uses a two-step data reduction. So we normalize our lead-lead ratios using something actually more homogeneous, so like a zircon or a glass, like a silica glass. And then we normalize our uranium-lead ratios using this carbonate, so WC1 standard or the RA138 standard. And we call this a matrix match standard for RA because it's the same matrices, the same mineral matrix as our sample. So here's just an example of what the data looks like. So the uncorrected data are plotted here, and they're given an age it's too old, so 287. And then we correct these data to the right age, 254. And we're talking about here 30%. then that's what we apply to all our samples in this run. We also run secondary standards, so we run generally at least 3 matrix match carbonates during each analytical session. So one is for the normalization, and then you have 1 or 2 more standards that you use to check for the accuracy and precision of that session. Why do we use carbonate standards and we can't just use zircon? Well, when we do ablation work, we do uranium and geochronology, we find that when you drill down through a mineral, uranium and the days will start fractionating away. And that's been well known since uranium in situ chronology came about. So here's just 3 different materials: zircon, silicate glass, and carbonate, and the ablation pits. And we can see that actually quite different depths can be reasonable related to 30 seconds. And if you look at the plots, these are just through time. It's actually the cycles and the mass spectrum on the x-axis and the measured uranium ratio versus the accepted ratio y-axis. We can see the zircon has an upward slope, and in the carbonate and the glass is slightly in the downward slope. So each of these minerals is drilling and uranium is fractionating. So to get accurate carbonate data, we tend to use a carbonate to normalize the session. So uncertainty propagation, calculating our uncertainties of our data points themselves and our ages is quite a complicated process. There's sort of some very simple principles, but the actual sort of steps we take and where to propagate different uncertainties is sort of nuanced, and it's quite clear that you can see papers that people do it differently, people apply kind of different approaches, and therefore the age you get, or the uncertainty of the age you get, can vary quite significantly. Me and my colleague were trying to work on a kind of updated paper on this, that I'm not going to talk about now. I think one of the key points is that uncertainties that you see in the literature aren't always going to be 100% accurate or true to that data. For example, this is a plot showing some raw data on the left. So this is the data for uncertainties. Basically, they come off the instrument. This is what you do see sometimes in literature: very big ellipses and a very small MSWD on your age. And that means we've probably overpropagated our uncertainties. On the right is something that's perhaps a bit more accurate. So we've got smaller data points, particularly in the data ratio. And an MSWD perhaps is reasonable. It's carbonate standard. So basically, care must be taken when doing uncertainty propagation. And also, care must be taken when looking at ages in the literature. For example, here's just one I just quickly pulled out this morning. Here's an age that I won't give you the name of, and you can see from here they've given you raw uncertainties that are read out from the software, and there is no propagation of systematic uncertainty from it. So this uncertainty here is probably a bit low. Probably should be a bit bigger. So what does limit the uncertainties and what does limit our age resolution? The analytical age uncertainty, okay, so that's going to be the uncertainty we get from plotting a regression and not worrying about systematic uncertainty. It's going to be dictated by the data point themselves. So each of these ellipses is one spot, and the size of those ellipses is going to relate to the signal that we measure in the mass spec. So giving more signal, it's a smaller ellipse. But if you've got a varying signal throughout that 30 seconds elevation, you're also going to increase the uncertainty. So the scatter about the lines, so the regression that's being used in geology, we tend to use MSWD. More scattered with bigger uncertainty, and also the scatter along the line. So, for example, if we look at these 6 different plots, on the left, on the top left, we've got a lot of data that's giving a nice regression, but then we have these points that are falling off the line. That gives us this high MSWD. If we look at the top middle plot, the data are kind of falling along a nice regression, but the data point uncertainties themselves, they're actually quite big, and that's giving us quite a big uncertainty. 10%. These data on the top right, they're quite radiogenic, but the data point uncertainties themselves are quite big as well, and we don't have much common lead data, so it's hard to draw a line. Again, we end up with quite a big uncertainty. If we look at the ones on the bottom there, we've got very little scatter. These data sit on the line beautifully, very low MSWD. But the data are, if you look at that plot, they're dominated by common lead. They're bright at the top there, the Busterberg block. We ended up with a 10% uncertainty for the precise data. Bottom middle, we're getting closer to something more rather ideal. So a nice line, quite a lot of scatter along the line that gives us smaller uncertainties for these intercepts. There's a little bit of scatter here, MSWD 2.5, so we get some data points still moving off the line. And on the bottom right, that's kind of close to the ideal scenario. So all the data fall on the line or very close to the line. The data points themselves are all very small, so we precisely measured those, and with a nice MSWD, and so we get a nice final position. In terms of the MSWD, what we call acceptable, what basically means the data give you a single event or a single population, represent a single age. There isn't a single MSWD that's still about. It depends on the number of analyses, that's shown by this diagram. Something to be aware of, and very few analyses, it's quite reasonable to pick a high MSWD. So when you've only got n equals 10, for 10 spots, an acceptable MSWD of 2 sigma is going to be 2 rather than 1. So people often think an MSWD should be 1, but it actually depends on the population size. And if you get to very large populations, a high n, you can see the acceptable range of MSWD are a bit smaller. So something that is very key to carbonate chronology, but actually relevant for all in situ lithology chronology, is that the systematic uncertainties can often dominate and control that final age uncertainty. What are those systematic uncertainties? They're basically uncertainties that we find not just to the data points, but to the actual age, to the final age. They basically don't change for each data point, they don't change for that session. They are fixed for that whole session. So one of them is the decay constant uncertainties, that's actually quite small. Another one is the long-term reproducibility and accuracy of that method. So basically, to determine that, one should gather data through lots of sessions across quite a long time and look at day to day, are we getting the same age or not, secondary standards. And then the uncertainty in the reference drill itself is actually quite big and quite important for carbonates. Just to give you some idea of these numbers, so decay constant uncertainty is about 0.1%. The long-term reproducibility, generally, most labs will achieve something no better than 1 to 2% over the long term, so it has to be incorporated. And the standards, the reference tool that most people have been using for the last 10 years is WC1. And that has a 2 sigma uncertainty of 2.5%. So that 2.5% has to be propagated on all ages. And this has quite a significant effect on the resolution of the ages we can expect. So these are just some made up numbers at the bottom. So this is a 1% age uncertainty, a 4%, and a 10%. And if we propagate these uncertainties, these systematic uncertainties, you can see how much the age changes by. So the top one, we had a 1% age. And once we propagated these quadratically, we ended with quite a big change. We went from 2.5 million years to 5.5 million years. If we already had a big uncertainty, we look at the bottom, we had a 10% uncertainty already. Once we propagated these, it's very small difference. From 0.5 to 0.51. Now, luckily, some labs have been working on some new standards, trying to find better materials. And RA138, which came up from the ETH Zurich lab, has a quoted uncertainty of 0.2%. So using this as a primary reference tool rather than WC1, will have a drastic difference on the age resolution you can see. So there's a whole bunch of reference tools out there, supplied by some various people, and there's a few that have only just been published this year, and some that are even just sort of in review. And the thing about, I should note about all these standards, is they're all kind of a calcite dominated matrix. So a lot of people want to take dolomites and have data dolomites. There's also anchorite, siderite, all these types of minerals. So there is a bit of a question mark over using calcite reference materials to normalize the dolomites uranium data. One thing that the ETH group observed in this study a few years back is that the ablation rate, so it's the ablation rate relative to WC1, the primary standard most people are using, does vary quite a lot. So we know that even with calcites, there are a variety of matrices types, starry calcites, versus micrite. And then we've got a few aragonites and aragonite and dolomites. looked at in this study, the ablation rate varies quite a lot for these texturally different types of carbonates, and that will probably have some small effect on the aging accuracy of the aging as well. The problem is, without dolomite standards, it's actually quite hard to kind of prove what kind of inaccuracy we might have. At the moment, everyone is kind of hoping that it's within the uncertainties of our ages. Just very quickly, just a couple of plots on why is laser ablation a useful method in combination with the old methods, the traditional method of light acquisition. If you look at this bottom left diagram, this coloured plot is meant to basically show some, imagine some sparry vein filling calcites, and it's coloured according to uranium concentration. So we're going to go from low to high, back to low. If we wanted to drill it out for isotope dilution, we have to sample quite a large volume, but then when we've done these are measurements, we have very small data points. So we might have 3 very small, nice tight, precise data points. But with only 3 data points on this regression, they might actually end up with quite a few exams. If, on the other hand, we did laser ablation work, we did a traverse of spots along this calcite covering all the low to high uranium domains, we might actually get a much nicer and more precise regression because we've got much better scatter along this line. So although these individual data points are much bigger than the isotope dilution, the regression is much better defined. So with this sort of spatial resolution, the ability to target low and high uranium domains and to get scattered along the mixing line of the isotope. That's why laser ablation can actually give precise aging. And the other downside of the traditional method is that when you're drilling out enough to get enough material to get lead from uranium, you're kind of averaging out the zones. You may in fact be averaging out the zones that we're doing ages. Is laser ablation accurate compared to isotope dilution? These are quite old data now. These are from Raspberry lab states, and the ID data are kind of showing what's line from just about 2 ellipses, and the bigger ellipses are the laser. These are 3 different samples. And in each of these 3 samples, the ID data sits within the ellipses. So that's good. And this is another study, pardon me. This was published by John Whitehead a few years back. And these are data. Again, we've got the red arrows pointing to the ID data and the big ellipses. So each sample is accurate with the answer. Okay, so that's about the methods and the integration in particular. And I'm now going to talk a bit about sample characterization and choosing areas of samples to hit. And this is very important for carbonates because they are very texturally complex. And finding the uranium can be pretty hard sometimes. Some carbonates will have low uranium throughout most of the area, and finding uranium is a bit like needle. Here's just an example of that compositional heterogeneity. So these are just laser ablation maps, vein fill calcites, each scale was a millimeter, and different types of donations. On the left, we see these kind of lines, high uranium, which are probably forming along cleavage. And the next one along, and it's quite hard to kind of understand what's going on here, but probably cutting this section across different crystal faces. These 2, the middle 2, are a bit more obvious what's going on. So you see this planar zonation or circular zonation when you're cutting across a plane of sparry calcite. In the middle of the vein, we'll have uranium at the edge of some of the grains, and then on the far right of the vein, with a simple decrease in uranium. Here's some more examples. So, dating speleothems has been very popular with uranium thorium dating, and it's becoming more popular now with uranium lead dating. But which layers are we going to put our laser on? Which layers are we going to drill out? The popular method is to phosphorate or the radiograph, and it picks out these uranium-rich layers. And you can see only certain laminae have uranium in it, or detectable uranium. And then if we go to a fracture fill example, this crystal or vein is going from the top to the bottom, and you can see in the uranium pot, we can see really drastic variation in uranium. So vein fill or fracture fill calcites often have 2 to 3 orders of magnitude variation in uranium. So it can be quite hard sometimes to target and find the highest uranium areas. It's the same sample, just with some ages, and you see if we date the area where the black area at the bottom, where there's very little uranium, big data point uncertainties, very poorly resolved age. And we've got 2 more traverses with ages, so we get more precise data points with the highest. So there's a whole range of different techniques that have been used to characterize our carbonates. And in this case, we need some examples used very quickly. So, often ignored or perhaps not utilized to its full benefits. Optical transmitted light really is a fantastic tool for calcites, particularly working in thin section. And if you have got thin section, working with 4 section scans, it's sort of like the first thing that you're doing. Reflective light, on the other hand, is probably a lot less used and less commonly used, but actually does really work quite well for porous samples, and if you're using samples in porous blocks, it's really great. This is a complicated vein sample. You can see the traverse these spots. And what you can see quite clearly the areas of blocky calcite versus the areas of fibrous calcite. So when you've got a good polished sample, the different textures come up quite well over reflective light. CL is perhaps the most popular technique, and rightly so. It really is a fantastic imaging tool. It has a really high resolution picking out zonation. And if you look at this diagram, it can often pick up things that this don't see with other techniques. So there's kind of a band of late alteration at the bright phase going through this material, cutting across. You just don't see without the other techniques. We'll see some more kind of examples of CL through the rest of the course. Backscattered electron is not so common. Of some carbonates and many carbonates, really often they're achieving that much zonation. These are some of the better ones I've seen. So these are individual crystals on the right, and they've got usual zonation. There's obviously quite a lot of contrast in elemental conditions to see that. And in this one, we've kind of got an initial vein cement, later vein. It's quite contrasting that you take across the backscatter. CCI, so this is a technique called charge contrast imaging. Again, it's a technique using secondary electron in SEM, and it's really good at showing slightly more structural and surface features compared to backscatter. Here's an example where we're zooming on the right, and you can kind of see that these planes are showing the crystal faces and how we're cut across them. So charge contrast is not used very often, but actually it's quite a useful technique. EBSD, again, a technique sort of growing popularity in the geosciences in general. So this is one of the earliest studies using in zircon, and it's starting to be used a bit more in carbonate space. EBSD has a wide range of uses. One is going to show you the angles of your crystal planes. So this is a vein of blended calcite, and if you look at the EBSD coloured map on the right, this is coloured according to the crystal angle. We've got all sorts of uses, and particularly if we're trying to date deformation and these states of deformation. One of the quickest, if you've got the kit, one of the quickest and easiest methods for mapping and characterizing samples is actually to use the laser itself. So laser ablation tracer mapping is quite a fast technique for analyzing regions kind of millimeters in size. So this is a map that would have taken probably 2 hours to do. It's kind of 6 millimeters by 4 millimeters. You measure a range of trace elements. On this occasion, we can see kind of areas of alteration. That's what this low magnesium black zone up here is probably a vein, a molten vein coming through the middle of these crystals. And we can actually target up here the high uranium zone. And this high uranium zone gives us a reasonable age, whereas if we have spots across the whole area, we get a lot of really scattered blocks. So whether you do this kind of mapping before your dating or whether you do it after your dating, there's a mixture of approach often taken. Mapping and tracing of images allow us to objectively screen data or objectively pick regions where the best data is going to come from. This again is some starry calcite crystals. We've done some dating across this, and if we do the tracing of the map, we see in the lead and uranium, in fact, particularly in the lead, there's bright zones of alteration veins cross-cutting. So if we exclude the areas of spot data where these veins occur, we get a much better age than just blindly having spots all over this crystal. So top, time of flight mass spectrometry is a technique. Again, it's growing in popularity, and there's more labs having this capability. The time of flight allows you to measure all of the elements, or as many elements as you want on the periodic table all at once, and the downsides are lower detection. This is recent, actually, 2024. This is a recent paper came out from Southampton lab, and these are corals, or that's a coral at the top and a coralline algae on the bottom. These should be useful from the maps. And I guess the big question is, what's the resolution for uranium and lead in these systems? If you can detect uranium, then it'll be a very quick technique for finding uranium hotspots within specific samples. Technique that's a lot more specialist is using the synchrotron or beam lines on synchrotron machines, and there's various different beam lines that people use for carbonates. So this one's called on-the-fly X-ray fluorescence mapping. We can see really nice uranium zonation in this carbonate, correlate that with the strontium zonation. Here's some other techniques using beam lines. So X-ray fluorescence on the left, and this one on the right is tender energy spectroscopy. So these pretty specialized and time-consuming techniques, but they can show some beautiful zonation and are really useful for detecting specific samples we want to look at in detail. And I'll show an example later on where you can look at uranium speciation using these methods. So carbonates are very compositionally heterogeneous. There's a wide range of methods to try and unravel these and try and interpret this heterogeneity, and then use it to pick areas where we're dating or to interpret ions. And as I said, carbonates typically have very low uranium content, and that's one of the reasons why this method is, I guess, one of the last commonly occurring minerals to be to have uranium lead applied to. A lot of the methods I've just shown you have very detection limits that can't really see the uranium. So how low are carbonates in uranium? This is a compilation I put together quite a long time ago now. These are all the carbonates I dated in the lab at the time. If we look at the median uranium values, you can see they're really quite low. So we're talking about 0.03 ppm in veins, or rich veins, and terrestrial veins 0.06 ppm, diagenetic slightly higher. So we're talking kind of ppb level a lot of the time for uranium, and the same with the lead. Speleothems a little bit higher. We're actually averaging almost 2 ppm on these examples. So detection limits are very, some instruments are 1 ppm, some are 10, some are 100. So that's one of the reasons that finding uranium is actually quite hard, and quite hard to screen carbonate materials. Often people ask, how much uranium do you need? It's not a simple question to answer. It's a bit like how long it's been streamed. It depends on the age of the carbonate, and it depends on the amount of lead, the amount of lead in that carbonate form. So this is kind of a slightly complicated diagram. On the right, I'm just talking through a couple of examples. When we use mu to give you, that is a unit that basically means the initial uranium over those contents of that sample. So if we had two different samples with a mu value of 2000, if we had one that's 15 million years old, on this diagram, this is basically a teravacilar plot, it's showing you the maximum amount of uranium that you're going to get. It's kind of going to fall from this part of the diagram. So we're talking kind of maybe 15% uranium index. So we're not going to get a very precise age out of that. On the other hand, the same sample that had a mu value of 2000, it was 150 million years old. In that time, we're going to have a lot more time to grow radiation lead from our uranium, and so the maximum radiation lead is going to be down here. So we might get a much more precise age now, getting much closer to the 40 years old. So this diagram is really just going to try to show that it's not just the amount of uranium, it's very much the amount of lead as well, and the older the sample, obviously the more lead forms into the so that is why, even though speleothems often are very young, the reason that they work really well with not just the high uranium, but also the very low K. So one of the things you want to do with this sample characterization is find uranium. But another thing people want to know is, you're sampling in the field or you're sampling in a lab, can we actually predict uranium in the context? Can you predict areas of high uranium? The answer basically is that this is still very hard to do, and there are very few methods to this, and it's very much still work in progress, and not many solutions to this stuff enough. So this slide has been in this talk for a version of this talk, I guess, many years ago, and at the time there was very little work on this. These are quite old papers now, in the 90s, I think it was 2005, and they basically found that one study found that tetravated uranium was found in calcite. So uranium has several different common species, the most common in nature are uranium-4 and uranium-6. And basically one paper found uranium-4 and another found uranium-6. And uranium-4 is a reduced species in natural groundwaters and natural environment, and uranium-6 is the oxidized species. And something else was what claims is that there's no examples seen with both species. So until really recently, the examples of uranium-4 and uranium-6, and we know a massive amount more than that. Luckily, over the last few years, there were more studies coming out published, more approaches, and this one came out. This basically is an interesting set of studies because this is actually carbonate formed in a man-made borehole. So this is Swedish boreholes looking at geological disposal facility. And because this is a man-made borehole, they can measure the groundwater, and they knew when the calcite formed, they knew when to drill. There's a lot of information on this calcite was formed in recent times. It's formed in the last 80 years at the time, I think. And they found uranium-4 in this calcite. A later study that's analysed this calcite and its system in a little bit more detailed found that it's actually what they think is going on with this calcite is that the uranium-6 in the water is being reduced to uranium-4 or in a microbial activity. Another study that's published earlier this year, again using the synchrotron techniques, so these are strontium maps on the left, basically found two different types of carbonate, or several types of carbonate that we found two different species. We found uranium-4 and uranium-6 within the same vein. So the result of these studies, I suppose, that ongoing work is, and perhaps my feeling is that often, particularly with vein carbonates, they often behave like little reduction fronts. And one vein, in other cases, like this vein is going to be a good vein, that vein is going to be a bad vein. It really depends on where that vein is within that oxidizing reducing system of fluid. In terms of lead, again, there's not really a massive amount of work in terms of thinking about uranium chronology, but we do know that lead substitutes for calcium into the calcite structure. So in terms of predictive tools, we're really struggling, really. There's a lot of work in progress going on there. And one of the problems with the trace element incorporation in calcite is just not driven by simple thermodynamics. There's a whole range of factors going on all at once, competing with each other. There's the trace element availability, calcite growth rate that affects the incorporation of elements, temperature, pH and EH, the carbonate and calcium ratios in solution, other minerals that are going to form compounds and form at the same time. All of these are competing to sort of determine and control how much uranium is being incorporated at any one point in time. So, but hopefully the future is bright. So what are some limitations of uranium-based chronology? I just want to cover two kind of things. This is a term you'll hear probably quite a lot when you start writing papers on this, open system behavior. It's another general term. It basically refers to decoupling of the parent and child isotopes. So basically loss or gain of uranium and or lead in terminal form. Like the causes, well, if we raise temperature enough, above what we call the closure temperature, we're going to start mobilizing these In carbonates, fluids is a big problem. They're very fluid reactive, and deformation can also help us mobilize isotopes. How do we recognise those consistent dates? This is really critical to understand and interpreting uranium-based dates and isochrons. Well, it's really subjective kind of subject matter. There's no strict rules, and really we try and suggest rules to apply to them. What does uranium mobility look like? These are real samples. So perhaps there's a mixing line. These blue points, and perhaps these grey points are suggesting uranium addition, which is goes to the right, uranium goes to the left. So this is just an interpretation. We don't really know. The key here is how to interpret uranium mobility versus something that might be a mixed age, an older age versus a younger age. Again, it's a bit more simpler to I guess, argue what's an outline in this right-hand plot. Again, is this a sign of uranium mobility? We really don't know. Here's a study I published where we basically try to point out what we thought some of this mobility might look like. So these are just two silicon fiber samples on the left and on the right. And the cathoding, in essence, the CO response varied quite a lot in these samples. So we have some areas of kind of planar or striping, some areas which sort of featureless mottled regions. Certain areas see sort of relic zonation surrounded by the mottled feature. So we think maybe we're getting recrystallization visible in these samples. We kind of see that again illustrated in the mapping. So the top is a slightly sparier, pristine looking sample. You can see some planar vertical stripes. We think it's a primary feature. And on the bottom example, where we have these kind of yellow off-color baylets, is where we have these hydrochloric zones. We think that's an alteration of each. And when we date these, the sparier, more pristine areas gave us the cleaner, the less scattered regressions in isotope space, whereas when we do spots across the mottled areas and the baylets, we get these scattered data. So we think on this sample we've seen signs of uranium mobility. But again, there's more tools really needed to work out on how to characterize this type of mobility within carbonate systems. Another problem that affects uranium is carbonate chronology is disequilibrium. I could talk a whole hour about this. I'm going to just skip across and give you a very brief summary. Essentially, if you want to date very young carbonates, say you're going to overlap uranium-4 in space, say 500,000 years, and you're talking 1, 2, 3, 4, maybe 5 million years, that's when you need to start worrying with disequilibrium. So isotopic disequilibrium between parent and daughter isotope during minimal formation. So we are generally measuring today today, and when we interpret our ages or calculate them, we assume that the secular equilibrium continues. But there are some kind of geological processes that can affect the intermediate isotopes. There are several intermediate isotopes between parent and child, one of them being 234 uranium, and we can get disequilibrium in that chain. That disequilibrium, that chain, the most biggest problem is 234 uranium, and you can get that in natural fluids, groundwater. And the amount of disequilibrium we see, particularly things like veins and porcelains, is really quite an unknown kind of topic. We can avoid disequilibrium, the 234 problem, by measuring the other parent, 235 uranium, 237, but that's actually very difficult for laser work because these isotopes are very low in the bucket. So I'm not going to talk about that in any detail, but please read the literature if you're going to take very young. Just to say, as these plots do, just to demonstrate how big a problem it might be. Here's an example of let's just say a sample that formed 4 million years ago. And if we had a normal, we assumed secular equilibrium, and we didn't do any corrections. That's fine, our sample of 4 million years is accurate. But if this sample actually had a 234 and 238 activity ratio of, say, 1.7, which is not unheard of, that is this histogram behind is just a compilation of global activity ratios for groundwater, travertine, and veins. So if we had an elevated activity ratio, our age would actually be 100,000 years younger than what we know. If we actually had a really high activity ratio, say something like 4, again, which is not unheard of in natural waters, our true age would have to be 3 million years. So a whole million year inaccuracy. So that's the sort of scale of the difference in the scale of the problem we might be dealing with. So one of the benefits of working with carbonates, we talked about several problems, one of the benefits is that the whole range of kind of compositional data that we can also obtain from this mineral. So this is kind of what uranium technologists who often call petrotechnology. You see this people using high temperature minerals like monazite and zircon. And it's basically the idea of linking our uranium lead data with imagery, with elemental and data from the same domains that we think. As I said, the good thing about carbonate is the whole range of systems we can use. So traditional approaches like delta-8 oxygen, delta-13 carbon. We've also got the using strontium isotopes. In the last kind of 20 years, we've had the development of Carbonate isotopes, which gives us temperature. And there's some sort of more esoteric things about the literature, like neodymium and calcium isotopes. And of course, something with the traditional method that's still really useful, although not so popular, it's still improving. So just to give you a few examples of these, here's an example of using elemental data to kind of filter our data. So this is a vein that's kind of full fracture sample, and we can see these kind of elemental maps show high and low areas. This is the cerium on the top right, and this is perhaps some primary zonation, and the minerals we disturbed by some secondary events. And if we take our data on the Vassilberg block, these data points are color coded by their cerium content. So if we kind of split them based on the cerium content, we can draw two lines here and interpret two images. The advantage of working on things like product sections is that we can do uranium dating, and we can also then drill out the same domains for Trump isotopes, and we can drill out areas for carbon samples. We can then kind of look at thermal histories and fluid histories of this rock. So we've got their age, and then we've got their precipitation temperatures. So we can compare the clump temperatures with the known thermalization of that rock. Carbon oxygen isotopes can be done by traditional kind of getting the powder from the sample by either drilling it or cutting it. But we can also do that in situ with an ion microscope. So these are on the left are complex crystals forming in the deep crystalline rock in Sweden, and each of these crystals we've done traverses with uranium lead. So this crystal is growing down to the right here, and we can see the age. The colour spots are coloured by age, so we're going from around 60 down to around 12 million years as we go along this growth zone. And we can have the same crystal that is analysed by carbon and oxygen. Ion microscope carbon oxygen isotopes. So we can kind of match the age with the fluid conditions. Again, the same thing on here. So we can see quite drastic change in this carbon oxygen plot up here. We start around 60 million years positive, and then we have a drastic change in the young carbon. We can also do the same thing with strontium isotopes. That can also be done by laser. So here's similar crystals from a similar area, and we're seeing changes in strontium isotope space along these crystals. So again, one of the benefits we're working kind of with these in situ techniques is we can combine a whole bunch of them within one sample. So here's one of my favourite fracture field samples. You see the hot already. We can take different traverses, but they're all kind of within uncertainty of each other. We can drill out several troughs and the powder. We get quantized isotopes. We've done traces and maps across this region, and then we've kind of cut out small slabs, take them to the ion probe, and then we have traverses with carbon and oxygen isotopes. So I want to finish up by just going through a range of the applications of this method, and give you kind of a flavour of kind of the literature. The diagenesis, being some of the high temperature background, I prefer to use Wikipedia for understanding some of these things. So diagenesis, what does Wikipedia say? Refers to the physical chemical processes that affect sedimentary materials after deposition of the form of forming. Now, diagenetic carbonates have really become quite popular in the last 5 years or so. So that's really because they're really important for understanding of what's going on in pore space, what's going on with fluids. So really useful for things like base evolution, trying to understand hydrocarbon maturation, migration, and now kind of turning that on its head and the carbon capture and storage. So a whole range of kind of applied methods, applied kind of uses for this technique. Here is one of the really early example of combining uranium isotopes with clumps, a really nice study. And so basically multiple phases of calcite and dolomite cements within this basin. So you can see that in this kind of paragenetic diagram on the left, really nice sequence of events. And then they've managed to date most of these with fairly precise constraints from the uranium lead method. And they combine these with clumped isotopes, and what you get then is a range of temperature time estimates. You can compare that with the estimated burial model of that basin. And when we have this offset, that suggests that there's a thermal anomaly within the basin. This is another very detailed kind of diagenetic study. And the reason I put this one in is really to demonstrate the complexity within cements that you might see in some alternative basins. So yeah, we're going to talk about 8 different cements recognised within this sequence. And you're only going to recognise these with really detailed CL microscopy. They've also done some pretty nice detailed in situ methods. So SIMS are carbon, as well as some strontium isotopes. And they compare that with the changing time. They managed to date 6 of these cement phases in uranium lead. And what that gives us is a really kind of nice time history of when these cements are forming in compared to what's going on at the basin, the pre-rift and the post-rift. Why does that matter? That's really interesting and important then for understanding the compartmentalization of fluids within these carbonate reservoirs and what sources of fluids are. This is a kind of similar study. Again, this one, what we're doing is they were trying to date actually the timing of the hydrocarbon charts. So some of the calcite cements within this setting, this is the pre-salt within the Namibia Basin in Angola. We can see bitumen staining within some of these calcites. So again, a diagenetic sequence, several phases of calcite and dolomite. And we can see that the calcite with the bitumen in has a data of around 86 million years, and that kind of overlaps more by volcanics. So we speculate there's some kind of relationship with the igneous activity and the hydrothermal charging. So there's a range of studies now looking at pedogenic carbonates. So pedogenesis is a process of soil formation, and pedogenesis is quite important for a range of different kind of topics within environmental science. Within chronology, it's useful for kind of stratigraphic constraints, because obviously paleosols are a really useful time marker, but also they tell us about climatic and environmental conditions. One of the earliest studies of this method was back in 2016. They dated these calcretes, dated paleosol calcretes, and that gives an important time marker for this sedimentary sequence. Same kind of thing in this paper, dating calcretes from a sedimentary succession, fairly young ones in this time, so we're talking about only 1 to 5 million years. And here they can compare the uranium lead constraints with the kind of estimated times age model from paleomagnetism. You can see they overlap nicely. So calcretes and paleosols are useful methods, particularly when we don't have other things, other methods available, such as dating of ash beds and times. This is a paper that came out this last year on paleosols, and again, slightly more detailed study this time. You can see the kind of calcite generations we're seeing with paleosols, and we've got a range of ages through this stratigraphy. And what's nice about this paper is trying sort of looking at what's going on in terms of how the precipitating environment is changing within this soil paleosoil zone. So moving on to brittle deformation, this is kind of one of probably the most popular popular area of applying the calcite or carbonate chronology method to date. That's because calcite is pretty common in thin tectonic veins, and we can use kind of veins and fracture fields to provide constraints on both fault movement and fracturation. And these are applicable to pretty much every tectonic section, compression or a strike set or an extension section. So these on the left are these examples, a range of examples of thin tectonic calcites. So classic kind of silicon fibers. Then we have kind of opening mode tensile veins, slightly more complex multi-phase shear veins, and some hydraulic breccias on the bottom, and cone formation on the front. So we want to kind of date calcites or vein fields and link them to deformation. And it's really important to understand how those veins are forming and when they're forming in relation to fault movement and or fracture opening. I put this diagram together just to kind of give some examples of the types of vein field that we see that calcite forms. And the idea is that on the left, when we have these kind of features, we can link them to fault movement quite confidently. When we have features like open buds, we can link them to the fault movement with low confidence, because the fluid flow that's precipitating this calcite could have come along much younger than when this fracture opened or before. And I put this diagram on the bottom right, basically to demonstrate that even kind of small, fairly innocuous looking veins can be highly complex. This 1 millimeter bedding parallel vein. If you're a fossil hunter and you know Staves, then this is just along the Staves beach, just south of the harbour. And these bedding parallel veins have been documented in terms of their structural history, but actually there's quite a lot going on in terms of stylolites, dissolution, fibrous and rocky calcite growth. So in terms of dating brittle formation, I put this example in again because I know a lot of UK people were familiar with Flamborough Head, famous kind of flip outcrops. These are just some different types of structures of data here, so kind of planar, opening mode veins. There are some silicon fibers visible on the fold structure, and then there are breccia zones with a lot of calcite cements in the meteorite fault zone, and then tensile veins with some nice coarse crystals. So we've dated as many of these different types of structures as we can, and build up the timing of the length going on. Again, I put this example in simply to demonstrate that quite simple looking veins in the field can be quite complicated when you get them under a microscope. The vertical vein again from the Staves, and we've got several phases of both fibrous and blocky calcite forming in this probably tensile vein. And we can date several of these and use a bit of different elements of composition. Here's this kind of same thing taken to the extreme. Here's a single vein, and they've managed to extrapolate 9 different veining or fault movement events or vein-fill events within a single vein. So, moving on from deformation onto stability. One of the, I guess, the technique that came along slightly later, application came along slightly later, is stability. When we first started dating carbonates, people asked, well, is it going to be any use for stratigraphic ages? Is it going to have enough precision? And the answer is there are sequences where carbonate chronology is certainly very useful. It's never going to be as precise as something like iodine and zircon, but it can certainly provide constraints to sequences that have debated or poorly known ages. So one of the first published examples, kind of some Precambrian carbonate chronology, is this one published from South China. So we kind of knew the range of dates we were looking at based on the trisal zircon and cross-cutting seals, and the best sample came out with an analytical precision at 1.5%, so that's pretty good. It's still 16 million years because this is a billion-year-old sample. And so this sample, or this data, is limited again by that standard, by the W1C standard, with a precision of 2.5%. So this would have been actually much better if we used a more precise standard at the time. Here's another example. So there's a lot of people, there's several isotope groups working on Ediaca and Cambrian carbonate sequences, looking at the explosion of complex life and the time of year process of carbon excursions. Here's an example from South China again, looking at the Cap Dollar Stone, and a pretty nice age with a pretty good precision, 636 on this carbonate. Can the carbonate methods kind of be used to define age models of stratigraphic sequences? This is going to be attempted in several areas where we have kind of constraints from other chronology. So on the left here is the Zircon-based depositional age model with a sequence within Argentina. And you can see their carbonate hosted model, although it's slightly more precise, it does overlap nicely with the Zircon model. So for many years, people also asked about dating ore deposits. And this came along, again, quite late. I think the reason being that the success rate was very low, and it's taken a long time for people to have good success rates with dating ore deposits related to calcite. These were two of the early examples. They're sort of slightly esoteric settings of mineralization, and they're dated a range of different carbonate types. One of the first carbonates I tried to date was from a lead deposit, and not surprisingly, it was full of common lead. And that led kind of to the assumption that dating mineral deposits with lead around probably wasn't going to be that successful. But over the years, a lot of papers have now come out in the last kind of 2, 3, 4 years, and it shows that actually success can be achieved. So this is an early study. This is an antimony system where they've managed to successfully date some different carbonate cements or some vein events. Again, this is another one. This is a carbon-type gold deposit in South China, a range of different calcite vein events that related to the gold formation or gold deposition and achieved some successful chronology. So over the years, as you can see, even in lead ore deposits, barium ore deposits, there are successful dates. So can mineral systems be dated with this method? The answer is yes. What the success rate is really an unknown, because people don't tend to publish their unsuccessful data, they don't publish their failed attempts. So although in the literature we can see the successful attempts, it's kind of hard to determine how many samples didn't work and what studies didn't work. There's a whole range of different other applications, some more esoteric ones, so kind of timing of microbial activity, and recently had a paper published where we dated microbial activity that's forming just after impact cratering. Speleothems is been very popular methods with the uranium thorium community, and is now becoming more popular with the later versions in the lead community. You can get pretty good precise ages even within the last, or within the Quaternary. Thermochronology, so with clumped isotopes, combination with dating, can we use carbonates as a thermochronometer? And finally, I want to talk about, just mention alternative isotopic methods. So we're talking about uranium lead, principally, but it's not the sole kind of isotopic system that's available within carbon. You'll see the literature, there's quite a few papers using neodymium. As far as I'm aware, most of these all of them use the traditional dissolution methods, so dissolving up different fragments or aliquots of carbonate and doing isotope dilution on them. Here's an example, actually the recent one, and you can see quite a nice isochrone. The limitation with this method is the same as with uranium dating. You're going to need a lot of variation in your scenario ratio within your carbonate, and you're going to need to be able to drill that out rather than just average all of that. Another method that's come along kind of recently is lutetium-hafnium. Lutetium-hafnium is a complex method when doing isotope dilution, but it is now achievable with ICP-MS with the kind of modern collision cell instruments, such as the triple quad and the collision cell mortar threat. And here's a study, the first studies that came out using in situ lithium hafnium. So this is on some ore deposits within Australia. The limitation with both these methods in terms of in situ or laser work is that they're really only applicable to very old rocks, because in terms of young rocks, we're just not going to have enough radiogenic isotopes to date. And they also need very big spot sizes and still tend to have pretty big data on uncertainties. So they're very useful probably for dating mineral deposits where there's very poor aging strength, rather than being used to kind of refine mineral systems models where we can already know the age. So what are some of the future questions and directions of the method? We still have a lot of way to go on understanding uranium lead incorporation in different carbonates and different types of settings. We still have a long way to go on understanding uranium mobility in terms of what temperature does and fluids and deformation. We have a lot of reference tools available, but we need them for different matrices, so different carbonates like dolomite. And we need to understand how those different matrices may affect the accuracy of some of our AGs. And there's still some way to go on understanding long-term usability. So if you just take an age and unsafe in literature, how reliable is that? If you measure the same carbonate on a different day, we can get the same age basically. I want to finish on this poem. So John Russell was a PhD student at the Oxford Lab, and he published some work on data metamorphism. And he wrote this poem, and all the work back then was type dissolution, isotope deletion. There was nothing for the lasers. But if anyone has actually tried this method and worked with uranium carbonates, then they'll understand exactly what this poem is about. Although it yields the dates you lacked, or any other data in fact, don't ever base a paper on a single datum monochron. The geochron is perfect for the dumb, the modest, and the raw, because even the utterly inept confines the slope and intercept. The scatterchron or errorchron defines the sort of polygon. Just choose an age, fudge a bit, and somewhere there's a perfect fit. The isochron is rather rare, but if you choose your points with care, rejecting those that don't fall on the line, behold, an isochron. So I will finish there, and thank you for listening.
That's great, Nick. Thanks very much. I particularly like the poem at the end. This is excellent. Questions, folks? There's a huge amount of information to take on board there. Lots of thank yous floating up the screen and clapping hands and so on. Nick, while people are deliberating, could I throw one at you? And far from any kind of expert in any of this stuff, but how does this compare to dating using micropaleontology methods, pollen spores, conodonts, anything like that?
I've not really seen much comparison, because I guess most of that is on the younger end of the timescale.
Yeah.
I guess at the moment I've not seen anyone publish an age. They say it's accurate within that uncertainty. No one sort of public, So the youngest stuff, has pretty big uncertainty. So it's not, I guess, or whatever other time scale you're putting on it would be by stratigraphic or astronomical. So far, everything is just sort of overlapped, and no one's really gone into much more detail than that.
Okay.
There is. I guess there are the stuff where it will come onto scrutiny. There's some opposing research groups working on the cradle of humankind, for example, in South Africa, and there, there is some debate over this age is wrong for this reason. But again, we don't have another method. Because we don't have another method to go to, it's sort of debated with no proof that one of them is wrong or the other or not.
Yeah, indeed. That's always been the problem with the micropal version as well, isn't it? To try and prove that that's actually the date. Yeah. Folks, anybody else got a question for Nick? I will be taking the video of this and processing it in the next few days, and I'll let you all know when it arrives online after Nick's had a look at it as well. And oh, here we go. Tom Arney. Tom, do you want to unmute and ask your question yourself, perhaps? Hang on. Okay. Okay, maybe Tom, sorry, can't get the mic to work. All right, let me read it out for you, Tom. Give me a sec there. What are the issues or advantages to dating young materials in the uranium, thorium, uranium, lead overlap?
Yeah, okay. Good question. So I guess the first thing is that uranium lead, uranium thorium has a maximum age. Depending on your analytical precision, it's sort of between 500 and 600,000 years. Can't go any older. Uranium lead, on the other hand, can overlap and get younger. And we did, so the first work we ever did was on stereothems, and you get reasonable precision on the uranium lead, even 200,000 to 300,000 years old. I guess the advantage of the laser is that at the time and for years we always just thought it would be a screening tool. So we screen with laser and then we go and do the hard isotope dilution work. All of that work to date, I guess, has shown that the laser is accurate with uncertainty for the ID. So that's one of the things, is that we think it's accurate within those uncertainties, but whether one is more precise than the other really depends on the young stuff, on your population size. So you've got 5 data points or 15 or 20 for solution work, or 500 or 200 for laser work. That really controls your precision a lot of the time. So that uranium lead is very quick. You can date several samples within a day, rather than several days for one sample. Again, I didn't talk about deuterium massive amounts. The biggest problem is for the 238 uranium system, and some papers came out, or one paper came out by Peter Vermeesch this year, arguing that 235 system is better and is kind of alleviates the problem. But then that doesn't really work well. I've tried several samples and it doesn't work in laser space. You just don't have enough signal, not enough counts. There are samples that it will work for on laser using 235 uranium and 207 lead, but you would need very fortuitous, high uranium and high lead as well, I guess, to measure. So and then laser ablation, uranium thorium, kind of got studied for several years, but the instrumentation is just not sensitive enough to really get anything with any precision to see it in the stuff with solution work. So I guess the answer is that each method has its utility, has its pros and cons, and we tend to need to use them all to either validate one another, or to some samples will work better for laser, some will work for the solution. So I guess all methods have their place. If that's sort of an answer.
Thanks. We have a question from Aditya Verma, which is, will this method be feasible for Paleoarchean or older Archean samples, which are highly deformed?
The older you get, you have more chance to grow. You'll develop more 3D genetic measure, so that's great. But it's all about preserving a carbonate. Then becomes a problem. We don't really have a good handle on how the temperature will affect the uranium in terms of a kind of diffusion. There are estimates, it's sort of 300, 400 degrees, but above that it's going to be problematic. But if you've got fluid around, it's going to be a lot lower temperature. So I think that part of the problem is just preserving any sediment older than the Archean or older. Keeping it below 300 degrees for 2.5 billion years is quite difficult. And I've worked on some Proterozoic sequences, and collaborators sort of say, oh yeah, their maximum bottom of the green sheet splashes are fine, but even then you can see recrystallization. So you said highly deformed. So I think as soon as you've got deformation, you probably will have fluids, and you probably will set the system. And then it's a case of, if you get a date, can you interpret what that means? So I think there is a limit, and it's not so much just because they're old. It's just a case of preserving carbonates becomes harder the older you get.
Okay. Thanks, Nick. Final one for you. Are there case studies, this from Peter Sorian and Ward, are there case studies of the effect of supergene events superimposed on older carbonate veins or sediments?
I'm not familiar in detail with anything on that, but I gather, I imagine there may be some people working on that. I mean, Catherine Moxon published a paper or two on porphyry deposits where she's detected several events. I wouldn't know. I don't think there's supergene, I guess, for that, but yeah, it's not my expertise. But I think people are moving into that field now. They're basically trying to use this technique to understand any carbonate precipitation events that are occurring within the mineral system. So whether that particular scenario has occurred, I don't know.
Right. Okay, thanks again, Nick. I appreciate you've given us a good chunk of your afternoon to present this, and no doubt plenty of time to prepare it also. So again, appreciate what you've done, and thanks a lot. We'll be in touch very soon.